Everyone, welcome to my YouTube channel. Today I am going to start a new series of lectures of linear algebra. In today's session, we will discuss about the external composition, internal composition, definition of field and the definition of vector spaces with examples. So let's start the definition of external composition. So our first definition is internal composition. Let A be any set such that A star B belongs to A, then star is said to be an internal composition in the set A. In the set A, that is, we have to take two elements of the set A and we will apply the binary operation star over the elements of A, such that the resultant element after taking the star on A and B should belongs to the A. If this type of condition is holding, then we call this composition as an internal composition. So let's take one example. For example, I have a non-empty set, the set of natural numbers together with the binary operation plus. In case of binary operation, if you want to know, you can see my previous video. That is the first lecture of group theory in which I have discussed about the binary operation. So we will take two natural numbers from the set of natural numbers and just apply the operation plus over them. I am taking 1 and 2, and after adding 1 and 2 we are getting 3, and 3 is also a natural number, so this element must belong to the set of natural number. So we have taken two elements from the set, and after applying the operation, that is internal composition, over the elements of that set, we are getting again an element of that set. So this type of composition is called an internal composition. So the only thing that you need to understand is just that you have to take two elements of the given set and apply the composition over them, and then if you are getting the element of same set, then the composition is said to be an internal composition. Let's take one more example. I am taking the same set, the set of natural numbers, together with the different operation, that is subtraction. If I take the same two elements 1 and 2 belonging to the natural number and I apply the operation negative over them, then 1 minus 2 is minus 1. That doesn't belong to the set of natural numbers. So what is done here, that we have taken two elements from the set of natural numbers and applied the operation negative over them. After applying the operation, the resultant element is not belonging to the given set. That's why this composition that we have taken, that is subtraction, is not an internal composition for the given set of natural numbers. So I hope the definition of internal composition is clear. Now we will move ahead and take the definition of external composition. In this case, we have to take two sets. So I am taking V and F. Let V and F be any two sets if A star alpha belongs to V, where A is coming from the set F and alpha is coming from the V. So the difference between these two composition is just that in case of internal composition, we were taking just one set and taking the elements of that set and applying the operation over the elements of that set, such that the resultant component were going to the same set. In this case, we will take the two sets and take the two different elements from both these two sets and apply the composition over them, such that the resultant element goes to the first set V. If this type of condition is holding, then we call a star as an external composition in V over F. For example, if I say that V over F is a set, that is, the first set that I have taken is V and the second set that I have taken as F, and this is an algebraic structure. I have discussed about the algebraic structure also. In case of algebraic structure, we take a non-empty set together with one or more binary operations. So I hope that you know about the algebraic structure. So this is an algebraic structure and I am applying the second binary operation over the elements of V. So I am taking one element alpha from the F, the set F, and one element from the field V, from the set V. So the resultant and the binary operation that I am considering as an external composition is dot. So alpha dot v is again going to the set v. If this type of condition is holding, then we called the second binary operation dot is an external composition. So dot is working here as an external composition. So let's take one example, R over C. The first set that I have taken is R and the second set that I have taken is C. We will work together with these two sets with the binary composition dot. So let alpha belongs to R. Alpha I am taking as a real number, and I am choosing one number from the set of complex numbers, that is iota. If I take the product with the binary composition dot over these two elements, then I got I dot alpha. But we know that this is imaginary component. Iota is an imaginary component that never belongs to the set of real number. The set which is outside, that is over which we are defining the set, the external composition, the product should always belongs to the external set. So this is not belonging to external set, that's why this dot is not an external composition. And we will discuss the concept of vector space, then I will tell you that this is not forming a vector space because this is not an external composition. This dot is not an external composition. Let's take one more example. If I take V as C, that is the set of complex numbers, and the second set F as Q, that is the set of rational numbers, and I choose an element alpha belonging to Q and V belonging to the set of complex numbers, then their product, because dot, I'm taking dot as an external composition, so alpha dot V is again going to C, because if you multiply any complex numbers together with the rational number, the resultant number will always belongs to the set of complex numbers. That's why this C over Q forms a vector space and dot works as an external composition. We will discuss about the definition of vector space in this video. So before that, let's discuss the definition of field, because we always define a vector space over a field. So definition of field is just discussed in case of ring theory, but we are not going to discuss the ring theory here. I am just telling you the simple definition of field. As we have discussed about the definition of group in case of group theory, that's why I will use the definition. I will use those definitions here, and I will write the definition directly. So an algebraic structure, that is a non-empty set composed of a non-empty set F together with two binary operation plus and dot, is said to form a field if F plus forms an abelian group and F dot forms an abelian group. That is the first composition, that is external composition. With respect to the external composition, it will form an abelian group, and with respect to the internal composition, it will again form an abelian group. If these two type of conditions is holding by the algebraic structure F plus dot, then this algebraic structure is said to form a field. So let's move to our next topic, and very important, vector space. Before discussing the definition of vector space, we need to understand the definition of external composition, internal composition, and the field over which we define the vector space. So let V be a non-empty set and let F plus dot be a field. The elements of F are called scalars and the elements of V are called vectors. Always remember that the elements of F are called scalars and the elements of V are called vectors. Then V is said to be a vector space over the field F if it satisfies some of the postulates or some of the condition. The first one is V plus is an abelian group. V plus is working as an internal composition. So we will take two elements from the set V and apply the operation plus over that two elements such that the resultant element is going to the set V. If this type of condition is holding, we say that our operation plus is working as an internal composition. So let's move to the property, because we are saying that this forms an abelian group, so we have to see that all the properties of group are holding or not. So we will move to the first property of the group, that is closure property. So we are taking two elements, and this is true for all elements of the set V. That is, for all u comma v belonging to V, u plus v is always going to V. From here we can conclude that internal composition is satisfied. The second property is associative. That is, if you take any three elements from the set V, they will satisfy this type of condition. Existence of identity. For all u belonging to V, there is an element 0, that is called zero vector, belonging to V, such that if you add zero vector with any element of the set V, this will always give you the same element. Here 0 cap works as an identity element, so identity is existing in case of V plus. Now the next property is existence of inverse. That is, for all u belonging to V, there exists an element minus u belonging to V, such that u plus, this plus is our internal composition, minus u is additive inverse of u, that also coming from the set V, and their combination with our internal composition will always give us additive identity, that is the zero vector. So this concludes the existence of inverse property. Now the last one, since we have said that this is an abelian group, so commutative law must hold. So the last property is commutative law. That is, for all u comma v belonging to V, V plus u is equal to u plus V. So if these five properties are holding, then we say that V plus is an abelian group. But this is not sufficient to say that V plus dot V over F is a vector space. So let's move to our next property. So our next property is external composition. So if V is closed with respect to, in this property we will discuss that V is closed with respect to scalar multiplication. What is a scalar multiplication? In case of scalar multiplication, we choose one scalar from the field F and one vector from the vector space V, and take their product, that is we will apply the external composition over that two element, such that the resultant element will go to in V. If this type of condition is holding, we say that our composition is external as well. So I am taking one element alpha belonging to F and one vector u belonging to this set V, such that their product alpha dot u is belonging to V. If this type of condition is holding, then we call dot is external composition. Now let's move to our third and last property, scalar multiplication and vector addition. In these properties, we will take two vectors. The first one, we will take two vectors and see the distributivity of scalar over the vector addition. These two vectors are added, so this is called vector addition, and we are multiplying it with a scalar, that's why it is called scalar multiplication. So this is just a distribution of scalar multiplication over the vector addition. Alpha of u plus v is equals to alpha dot u plus alpha dot v, and this is true for all alpha belonging to F and for all u comma v belonging to V. Similarly, if we take the scalar multiplication over the vector addition, scalar addition over the vector multiplication, this will also hold. That is, alpha plus beta dot u is equals to alpha dot u plus beta dot u, and this is also true for all alpha beta belonging to F and for all u belonging to V. Now with respect to the external composition, we will also see that the product of scalars together with the vectors is associative. So that's why alpha beta dot u is equals to alpha dot beta u, and this is also true for all alpha beta belonging to F and for all u belonging to V. Now the last one and the most important property, 1 dot u is equals to u. This is true for all u belonging to V, where 1 is the unit element of the field F. Every field contains unit element, and those fields which does not have units are called field with no units. So every field has a unity, and if we multiply this unity, that is we take the external composition of unity together with the element of u, we will always get the same element of the vector space. So these are the properties of a vector space. If these conditions are holding, then we call V plus dot is a vector space, and we also write it as V over F and read it as V over F is a vector space. Vector space. So I hope the definition of vector space is clear, and now I am going to discuss the example R over R. This R is a non-empty set, and I am defining it over the field R forms a vector space. So we have to check all the properties of vector space. So in that series, the first property is R plus is an abelian group or not. So firstly, we will discuss the first property, that is closure. For this property, we will take two elements belonging to R such that u plus v belongs to R. This is closure property, and this is also called external composition. We are taking two elements from the set R and applying the internal composition over these two elements. Then we are seeing the resultant element is also going to the set R. So this is holding the internal composition. Now we will move ahead the associative law. The third one is existence of identity, that is for all u belonging to R. This is bold R. This represents the vector space, that is the set that we take outside. So this is bold R, and the elements that belongs to this bold R are called vectors. So I am taking this example as R over R because every field is the subfield of itself. That's why we can define a vector space R over R. You can also define Q over Q, C over C. So let's move to our property, that is existence of identity. For all u belonging to R, there is an element 0 cap. This is called zero vector belonging to this bold R, such that if you operate internal composition of this vector with the 0 vector, you will get the same element. So this 0 vector works as an additive identity here. Next, existence of inverse, that is for all u belonging to R, you will get an element that is the additive inverse of u belonging to R, such that if you apply the internal composition over these two elements, you will always get additive identity, that is the 0 vector. Now let's move to our last property of this property, that is R plus is an abelian group, that is commutative law. That is for all uv belonging to R, u plus v is equals to v plus u. Now the next property is external composition, that is R is closed with respect to scalar multiplication. In this property, you will choose one scalar from R. This is not a bold R because we are taking it as a field, and this is bold R, such that their product, that is if we apply the external composition dot over these two elements, it will belongs to the vector space R. Now the four properties that we have done, that is the scalar multiplication and vector addition, that is if you add two vectors and apply the scalar multiplication over them, then you will get alpha dot u plus alpha dot v, and this is true for all alpha belonging to simple R and UV belonging to bold R. Similarly, this property that we have done, and similarly this, the last and most important property is it that 1 dot u equal to u, and this is true for all u belonging to bold R. That is, if you take any unit element of the field F and take the external composition of this element with any element of the vector space V, you will always get the same element. To check that whether the given set is forming a vector space or not, we will always apply or check this property. So this was the definition of R over this was the method to show that R over R is a vector space. I hope you guys understand this, and I want to give you some homework so that you can also try by yourself. So for practice, you can consider these examples, that is C over R forms a vector space. This is the set of complex numbers over the set of reals, and this is R over Q, Q over Q. These all forms vector spaces. With these, by showing these all properties, you can show that these also forms a vector space. So in our next video, we will discuss some more concepts related to the vector space. So till then, please like, subscribe my channel. Thank you.